It's the AEMT lecture series. Welcome back. This will be video number 2 for chapter number 13. Alrighty. So video number 1's in the book. So now let's continue with the chapter for video number 2. So we're going to talk about body fluid composition and compartments. Fluids found in the body are composed and of dissolved elements in water. Okay, so a solution has two things to make a solution. You need a solvent, okay, and then you need a solute. Okay, so think of a solvent maybe like a sugar cube, and think of the solute as like, water. And so the solvent's going to dissolve in the solute. Electrolyte movement and balance. These electrolytes balance themselves based on charges, right? And when we're talking about like positive charge and negative charge, and they usually will balance themselves on either side of the membrane or the cell. When we're talking about the balance, has two components: balance of a compound on either side of the cell membrane, or the other component again would be the charges. Materials flow from an area of higher concentration to one of lower concentration. We've heard that before, right? It's called diffusion. And it's literally no different. Like I said, oh man, every time I try this, something always kind of gets jacked up. Let's see. So here you have like a beaker, and so remember if you took if you had a water bottle and you were going to put one of those flavor packs in, right? And you drops in here, it's going to dissolve and it's going to change this whole color. Maybe you put it's water, you put like a cherry type stuff in there. It's going to change it all to cherry, right? That's simple diffusion. That's what all we're talking about from we're moving from an area of lower concentration to higher concentration. I'm sorry, higher concentration to one of lower concentration. Okay. Filtration. All right. So when we talk about filtration, we think of the kidneys because they're the biggest filter that we have. And what ends up happening is this can also happen in the capillaries as well. And basically what you have here is you have your water and you have your particles, right? And what filtering is that it gets to a point to where the particles separate. The particles get taken out, but your solute, or water in this case, continues to flow. And that's all it is. We're talking about filtering. It's a type of diffusion used by the kidneys to clean blood. And again, it can happen in the capillaries too, because what happens in the capillaries is gas exchange, basically, right? We have our capillary bed in the pulmonary system, Right there at the lungs, we have the capillary bed where the alveoli and all that are. But this can, so you have a blood vessel here. Right, what happens though? An artery turns into an arteriole, becomes smaller. And it gets so small that the particles just kind of get trapped. In this case, it could be gas exchange. Okay. But the fluid is but the fluid that carried the CO2, right, inside the red blood cell, it's still fluid, and the fluid continues to flow. Okay, so I had to pause you there for a second, guys. I'm sorry, I had somebody come in the office. So we were talking about filtration, right? So water carries, and we said the kidneys, and then we talked about at the capillary level that can happen too. All right, so active transport. The thing to know about active transport is that this is going to happen when diffusion can't happen. Okay, when the cell membrane is selective and it will not allow for diffusion. So then we have active transport. And the thing about active transport is, in relationship when you're comparing it to like diffusion, is that it's not free. Active transport is going to cost you some ATP. Diffusion doesn't cost anything. It's usually, it's just going to happen. Just like water floating down a river, it's going to go with the current. Active transport is a lot different because when we're talking about active transport, we generally think of the sodium-potassium pump. And you'll notice that sodium is a cation, and so is potassium. They're both cations, and they're both pretty happy where they're at. So we have to change it up in order to get those two cations to do what we want them to do. And that's where active transport comes in. And so that's what you need to know about active transport. It's a method used to move compounds or to create or maintain an imbalance of charges. Again, we need that imbalance of charges to get to that action potential. We need that automaticity to occur, and so we had to have that mismatch of charges. Okay. Osmosis. So osmosis, right? Let me turn over to my notes here so I can keep up with where we're at. Okay, I think I'm there. Yeah, I am. Okay, osmosis. So when we talk about osmosis, we're talking about the movement of water across the cell membrane. Okay. This occurs because there's different concentrations on each side of that membrane. Okay. Could be a concentration of sodium. It could be a concentration of whatever. But there's different concentrations, and they want to equalize, and they just naturally want to equalize. Osmosis is usually, the difference in osmosis is usually going to be well, I don't want to say it like that. The difference between osmosis and diffusion. Let's say that. So diffusion is moving like a solid particle across the same, that's it. Diffusion is moving a solid particle, and it accomplishes the same thing as osmosis. Osmosis, though, is different because we're talking about moving water. We're not talking so much about moving solid particles. So I hope that makes sense. But they're the exact same thing, minus those. Minus one is diffusion, meaning solid particles. That's pretty much it. Increasing the concentration of sodium in the extracellular fluid decreases the water in the fluid. Water moves out of the cell to create a balance of water molecules and to dilute the increased concentration of sodium. So what I'm saying there is water always follows sodium. Okay, so if you have an increase in concentration of sodium and it's outside the cell in the extracellular fluid, okay, so then that's going to eventually decrease the water inside that cell. Water is going to want to move outside because that's where sodium is. So let me draw it out. All right, so there's your cell. Let's draw a little cell membrane here. Okay. So let's say you have sodium here, it's outside of that cell. And we'll say we have potassium in here. Okay. And there's always still a little bit of sodium in here. The sodium potassium pump will bring in more sodium, but it doesn't actually take all the sodium out. There's still some in there. And so what happens is when sodium's outside the cell, there's more sodium out here. So let's put a number on it. Just put 100. We're going to say 25 here. So as long as there's more sodium outside the cell, you're going to have a shift of intracellular fluid coming out, becoming extracellular fluid. Okay? That's all that's saying. That water will always follow sodium. Okay? All right. Osmotic pressure. Are we already there? Let's see, we talked about diffusion. We talked about filtration. We talked about active transport. We just talked about osmosis. We talked about the difference between osmosis and diffusion. So, osmotic pressure. All right, so osmotic pressure is an increase. It's an increase balance of volume that puts pressure on the cell wall. That's what it is. So, all right, so what we have here is maybe we have something going on to where we have more sodium in here than we're supposed to. And what that's going to do is going to put pressure here on that cell wall. All right, and that's what it is. That's osmotic pressure. It's an increased balance of volume that puts pressure on the cell wall. Okay, so it drives metabolic functions. Let me go down one here. So yeah, so when we increase the concentration of sodium, and if I'm reading the right note, osmotic pressure increases the balance of volume, puts pressure on the cell wall. That's it. There's another definition that we need to understand. It's called tonicity. All right, so tonicity of the solution. It's going to basically mean the effect of osmotic pressure on a cell. Okay, so if we have a concentration of sodium in a solution and the movement of water in relationship to the sodium levels inside and outside the cell, that's what it means, tonicity. So it's the concentration of sodium in a solution and the movement of water in a relationship to the sodium levels inside and outside the cell. And so tonicity of the solution affects the osmotic pressure on a cell. And that makes sense from what I just showed you. Because of the sodium right here, we have more sodium inside. The more sodium we have, the more water we're going to draw in the cell. And that affects tonicity. Okay. So let's talk about solutions. So the first one, let's talk about isotonic. All right, so here we have an isotonic solution and its effect on a normal cell. And you'll notice has no effect. And that's because it has the same concentration of sodium as does the cell. Okay, water's not going to shift inside and it's not going to bring water outside. It basically is just going to bathe that cell. That's all. Hypertonic solution. So a hypertonic solution, let me see if I can write on here. No change. All right, so a hypertonic solution, it's an increase in the concentration of sodium. Okay. So what we're going to have here, so we have an increase of concentration of sodium outside that cell. So what happens? So water is going to be drawn outside the cell. Okay. And it causes that cell to shrink or collapse. Okay, that's what hypertonic means. So the cell may collapse from an increase of extracellular osmotic pressure. Okay, why? Because you have pressure being put on that cell coming from extracellular, and it's just pushing down on the cell. The water's being drawn out. You have an increase in extracellular osmotic pressure. Remember, this is intracellular fluid. This is extracellular fluid. And so you're going to have an increase extracellular fluid osmolarity. Now if we look at hypotonic, So hypotonic means you're going to have a decrease of concentration of sodium outside that cell. Okay. So you're going to have a decrease of sodium. And what's that mean? Well, the sodium's in here then. It means that water is going to rush into the cell. And so you're going to have an increase of intracellular osmolarity. Okay, and if this cell burst, whatever, but you know what I mean, called lysis, the cell lysis. That makes sense? Because this is important because we're fixing to talk about fluid compartments and what this fluid, how it moves around, and all of that. All right, so let's just hang on. Hypotonic solution has a lower concentration of sodium. Okay, so let me put, I'm sorry. Increase sodium here, decrease there, no change there. And here, sodium's hanging out here. Increase in sodium here, and and low sodium here inside the cell. Got it. All right, let's move to the next. All right, fluid compartments. It gets kind of confusing when we talk about this. It doesn't have to be. I'll try to keep it simple. But even I find myself getting confused sometimes on it because I think too much into it. But so water can be what? It can be intracellular inside the cell, like I just showed you, or extracellular outside the cell. There's mechanisms in place by the body called homeostatic, just like homeostasis. Homeostatic controls mechanism to ensure that balance is restored. And your body's circulatory vascular system functions as a fluid highway. I'll show you that. Okay, I'll bring over our chart here. All right, so here we have, this is in the book, this picture's in the book. We're talking about the circulatory system being the fluid highway, and it is. Remember that plasma, is 98% water, so that's what we're talking about. Okay, and so this right here is your intravascular. Intravascular. Okay, that is one compartment. Okay, that's your first compartment. Now, we have to remember that there's ways that this plasma, which is 98% water, can get thrown out of here, right? And we have talked about increase in afterload before. And so what we have to remember is the circuit. Okay, so Here's your heart, right? And so this is your aorta coming off, bringing blood around. And back up into the right atrium. Remember, it's like a big circuit. I'm just going to draw a little box here. Okay, so inside it's pressurized. That's how everything gets moved around. It's moved around. We know that we have cells down here, right? And we know that we have that O2 CO2 exchange, so the cells get, systemically fed. We know that blood's going to come up here, dirty blood's going to come up here, right atrium, and then it's going to go through the right ventricle, pulmonary valve, pulmonary vein, out here to the lungs to get reoxygenated, right? It's going to drop off that dirty blood, pick up clean blood that's full of O2, and that's how the process goes. Well, certain conditions, right? Congestive heart failure being number one, causes this left atrium to grow. Preload's been increased. That means we have blood that is coming down here at high velocity. High velocity. So when we look at it like that, high velocity, the left atrium is contracting hard and fast, and when blood comes up over this aortic curve and just dumps down like water hammer, right? Remember that? We talked about a little bit of water hammer there. Well, so this being your, we'll use blue. All right, so here's your intravascular. This is the membrane right here, right? What can happen is in those smaller arterioles where the vessel becomes smaller, it can't handle the volume. Okay, can't handle the volume of blood coming out at the velocity that it's coming out. It can handle the volume, it just can't handle the velocity. And that ends up leaking out of the membrane. Okay, leaking out of that membrane, right? And this space right here that I just drew that blood or plasma water busting through that membrane. Now remember, it won't let the blood cells out. They're too large to get through. So your red blood cells are still there, right? You still have all your platelets, red blood cells, white blood cells, but the plasma, the water, is being kicked out because of the velocity, right? So that velocity is called its increase afterload, and it's dumping into the interstitial space. That's compartment number 2. Your interstitial space. Okay. Compartment number 3 is going to be your intracellular space or compartment. Intracellular compartment. That's this right here. All right, so you have intravascular, interstitial, and intracellular. What's unique about the interstitial space here? It's like a buffer. No, maybe buffer's not a good word, but it's like it can help out, because if the vascular space starts becoming low, it can send fluid from the interstitial space into the vascular space, which is helpful if you're losing blood and that sort of thing. Okay, so it has the ability to do that. We'll talk more about that. All right, so the body, we said, had that homeostatic control. Okay. Fluid compartments, we talked about the intravascular. And also notice that it's called extracellular. Okay, that extracellular. The interstitial, also called extracellular. Right, and then you have intracellular, and that's actual inside the cell. The extracellular compartment contains, okay, so extracellular, it contains fluids that surround blood cells. We said the interstitial fluids are outside the vascular system and also between other cells. I think I showed you that, but just in case. So this is all interstitial space in between these cells. Okay. Extracellular fluid occupies any area that is not inside the cell. Extracellular fluid compartments act as conduits for transferring gases and nutrients between vascular and interstitial fluid compartments. We'll talk, well, probably can show you. And basically what they're talking about is that happens here because this area, a lot of times they filter in that area. All right, so extracellular fluid levels are regulated by the presence of sodium. So if there's sodium out there, that's going to get crowded because water is going to follow that sodium out there. It accounts, extracellular fluid accounts for about 16% of your total body weight. It's a microscopic spaces between those cells. That helps to move water freely between cells and vasculature. Okay, I mentioned earlier about capillaries. You know, that's where perfusion occurs. And then intracellular fluid. Okay, it's going to be within all cells. And large proteins within the cell can draw fluid into the cell. Okay, and so water surrounds all cells. The body again will adjust to changes in balance in between intracellular fluid and extracellular fluid. And the reason why it's important to know all this is because you're going to be dumping fluid in people, and you got to know what's going on with the fluid. You got to know where it's going and how it's going to affect the body. Okay, and when we're talking about intracellular fluid, those large proteins draw fluid because of their overall negative charge or positive charge. Okay, so it can not just sodium, but it can also draw fluid based on charges, and that comes from H2O, 2 hydrogens and an oxygen. and those hydrogens are positive, your oxygens are negative, so it can still draw it in that way too, and it does that through homeostasis. And the feedback system is just that. I mean, it's just a feedback system through the nervous system, checks and balances. Okay. Dehydration. All right, so it's defined as a total depletion of the system's fluid volume. Okay. Let me slide back over here. So let's look at it. So dehydration, right? So yeah, it's a depletion of the body's total systematic fluid volume, and we have fluid loss from the vascular compartment. All right, so your fluid loss is coming from here, the vascular compartment. But I'll show you here in a little while that it can be from other. It can actually can be from other compartments. But what happens is remember your plasma, your 98% water has been depleted. Now that it can draw upon the interstitial space. I'm just going to put IS. Okay, it can draw from that if it needs to and bring some fluid back in, but it's not a quick process. Overhydration. So overhydration. So example of that would be like we fluid overloaded somebody. So what you end up having is a full vascular system. It's full. What do you think's happening? It's dumping out here, isn't it? It's dumping out into the interstitial space, right? And depending on sodium levels, it could either be drawing fluid into the cell or out of the cell. Dehydrations, it's more, when we're talking about just dehydration, more common in older and younger folks. Dehydration forces a shift of fluid from that intracellular to the extracellular compartments. And, there's a whole range of reasons why somebody can be dehydrated. We talked about overhydration. And overhydration, for the most part, you're going to have your edema, right? Crackles, just like CHF symptoms. All right, IV fluid composition. So we're going to talk about our IV fluids. So compounds and ions dissolved in the solution are identical to the ones found in the body. Okay, each solution is a concentration of solute and solvent. Okay. Sodium is the benchmark. Okay, and we know why, because water follows sodium. And a common fluid that we give is normal saline. And there's a reason for that. and we'll talk about it in just a second. All right, so let's go back and talk about it now. The reason why is because normal saline, NaCl, okay, is 0.09% sodium. And it just so happens that that matches perfect with the cell. Okay, so we're not going to be drawing from that cell when we give normal saline. And that's what we need. Our fluid needs to be all intravascular. And that is why. All right. Crystalloid solution. Okay, so it's a solution of dissolved crystals. Okay. The crystalloid solution has an ability to cross the cell membrane. And so that's a good thing. We need approximately 3 milliliters of crystalloid solution to equal 1 milliliter of blood. Okay, so it's a 3-to-1. 2/3 of an isotonic crystalloid. Isotonic meaning it's equal to the sodium inside the cell. Okay, we'll leave the vascular space in 1 hour. Remember that it has 0 capacity to carry oxygen. And what we do is we usually give a 250 milliliter bolus or more, but we're just trying to achieve a radial pulse. We're not trying to get a great blood pressure here. And what do you think that why do you think that's the reason that we're just trying to get a radial pulse? We know that a radial pulse is going to give you a systolic blood pressure of 90 millimeters mercury. So why then? Why are we just trying to get to 90? Why don't we try to get to 120? Well, the reason why that is because of the little story I said in the first video. We don't want to dilute the hemoglobin that we have, and we don't want to dilute the body's ability to clot. Those are the two things. So that's why we're going to be careful about how much saline we give. We just need a radial pulse. That's all we need. Let's see. That's okay. Next one. Colloid or colloid solutions. I call it colloid. I don't know. All right, so these usually contain molecules that are too large to pass out of the capillary membrane. Okay. All right, let me back up. Let's talk about, let's look at this real quick. So back to crystalloid. Back up this one. All right, so what do we have here? So we're basically filling the vascular space. And that's what we're achieving here. Now, it will leave this vascular space and start moving to the interstitial space right there in about 1 hour. Okay, and it crosses over the cell membrane. So it can cross over the cell membrane very easily. So if for some reason our intracellular fluid is low, it can refill that. Okay, and so that's what crystalloids will do for you. Now we're going to talk about the colloid. All right, so your colloid solution, what's it going to do for us? All right, so it contains molecules too large to pass out of the capillary membranes, therefore remaining in the vascular compartment. All right, so this stays in the vascular compartment. Here's our vascular compartment. It cannot transfer out. All right. Has a high osmolarity. Okay. So it's going to be putting a lot of pressure on the walls here. It draws fluid from the interstitial spaces. It's going to draw fluid in. All right. And this is good because think about what I showed you earlier when we have an increase in afterload. All right, and I should have said this earlier. We had an increase in hydrostatic pressure, okay, from your CHF patients. Remember I said that that plasma is gonna leak out here into the interstitial space. Okay, so we can give this a colloid solution, right? And if we have a congestive heart failure patient, it'll start drawing that back into the vascular compartment, therefore reducing edema. Okay. It's also going to reduce edema from your, like I said, from your pulmonary, but also cerebral, or your brain, right? Your brain tissue. Which is a good thing, right? And some of the things, some colloids are called albumin. If I had you for EMT school, I said it, we talked about it. I know you probably don't remember. You'll swear I never mentioned it, but I swear I did. Right? Whole blood is considered a colloid. Okay. Oh man, email's going crazy. All right. Let's come off here for a second. So that's your colloid solutions. All right, isotonic. So it has the same osmolarity as serum, like same osmolarity as serum is like the serum part of the blood and other body fluids. It expands contents of the intravascular compartment without shifting fluid to or from other compartments. Lactated Ringer solution is generally used in the field for patients who have lost large amounts of blood. So isotonic is what we use here. in the field. Okay, and so basically what we have here is we'll have this stuff, it's gonna stay in the vascular compartment. Okay. It's not gonna draw from here. Okay, like the colloids do. All right, it will not draw from interstitial. It will not draw from cells. And so what we have here in this case is 0.9% sodium chloride. Or NaCl. Okay, that's one. Or you may see it as a LR, lactated ringers. Now, just special note about LR, we don't carry it. I don't think we carry it here anymore. Contains something called lactate. Okay. And lactate has to be metabolized by the liver. All right. And so what lactate does is like a buffer to combat the intracellular acidosis from blood loss. But if your patient has a history of liver disease or liver failure, they can't metabolize lactate. And so that could be a problem. But other than that, lactated ringers is good. All right. Hypotonic solutions. Lower concentration of sodium than the cell. They hydrate the cells while depleting the vascular compartment. Let's look at that. Okay, so why would you need this? So why would we need this? Right, so let's talk about it. Okay, so water's gonna, if you give this hypotonic solution, it's gonna enter the vascular space. Okay. But it's not going to stay there, is it? It's going to go out here to the interstitial fluid compartment. Okay. So why would we want it? Why would we need something to leak out here? Well, I'll tell you why. So a lot of times what happens is you'll have a patient who has history of renal failure. Okay. And what's going on here is that they have plenty of vascular space fluid, plenty of it. All right, their blood pressure, let's give them a good blood pressure. Let's say they're 170 over 90. No, let's change it maybe to 170 over 50. That's better. All right, so we got problems. 170 over 50, right? But that's because these cells out here are dehydrated. Okay, they're dehydrated. There's nothing to pull from in the vascular space, but the vascular space doesn't need it because it's already full. And so what happens is, like after dialysis, you'll see this. And so they need fluid. Their cells need fluid. Okay, they're shrinking, and there's probably a high amount of sodium out here anyway, though. Their cells need to be rehydrated, but we don't need to rehydrate the vascular space. So we can give a hypotonic solution and achieve that. We can achieve cellular hydration. We can also see this in hyperglycemic patients. With diabetic ketoacidosis. You have an increase in glucose that's that glucose is drawing the fluid out of the cell. And they're very dehydrated, even though their vascular space is full. Okay, so a lot of times we'll give them a hypotonic solution. Now, there's problems with this. Right, because of that shift of fluid from the intravascular space to the cells. If it happens too fast, it can cause cardiac collapse. Right, it can cause collapse from here and eventually, the cardiac. It can also, so let me put cardiac collapse. Can also increase intracranial pressure. Right, so we really don't need to give this to a patient having a stroke or head trauma. All right, and so then a problem arises when we talk about fluid called third spacing. Third spacing. All right, and so what we'll see this in is a patient who, a lot of your burn patients have third spacing. And that's where you have an abnormal fluid shift into the serous linings. Okay, and the serous linings like membranes of organ systems. So I'm just going to, you can use, I guess I'll use the heart, but every organ has this serous lining. It's very, very thin. It's microscopic to a point. And you have so much fluid that it starts getting in those serous linings and causing problems. Okay. And so we can't use a hypotonic solution for them. Okay. Not for burn patients. We can use other things. So no hypotonic solutions for them. All right, and last on our list of IV solutions anyway should be hypertonic. Hypertonic solution has more ionic concentration than serum, helps to stabilize blood pressure, increase urine output, and reduce edema. It's rarely used in a pre-hospital setting. And so that's going to pull fluid hypertonic solution. It's just body fluid into the vascular space. Okay, so we're going to be taking from the intracellular and interstitial compartments. All right. That's going to be it for this video of video number 2. Let's see how many minutes. We've been going for a little while. So I will make the 3rd video here shortly. And until then, look forward to talking to you.